learningmeasure.tv. Science and engineering podcast with emphasis on measurement. Brought to you by David Archer and learningmeasure.com. Episode 1. Periodic Phenomena. Hello. I'm David Archer. I'm the owner of learningmeasure.tv and learningmeasure.com. And this is episode 1. In this episode, we're going to do a review of an open source graphics package called xmgrace. We're going to have a short tour of the learningmeasure.tv website, and our feature part is on periodic phenomenon. But first, we'll be right back after this. One of learningmeasure.tv's sponsors is tradepub.com. Tradepub.com is a site where one can sign up for a large number of free trade publications. If you'd like to support this podcast, go to the learningmeasure.tv site, scroll down to the free publications link, and choose one of the magazines or one of the publications or one of the categories and sign up through that link. Each publication subscribed to through this link on learningmeasure.tv website helps keep Learning Measure TV on the air. Thank you for your support. The other day I was preparing some graphs put in a publication using an open source tool called xmgrace. The thought occurred to me, this is a useful tool that people who would be watching this podcast might want to be interested in. So then I thought, well, maybe it's worthwhile to put some sort of software tool that could be used to interpret or analyze data as a regular feature of this podcast. Well, here's our first attempt. The software xmgrace is open source free software that runs under X or X Windows. Now, X Windows is an open source windowing environment that can be run under Unix or Linux, Mac OS X, or even under Windows. We're not going to talk about how you install X, although if you are interested, we have provided a course. If you go under your student account, the course catalog, we've created a new section, open source software, and you can look under, take the course xmgrace 101, which will go over things like how you download and install and where you can get X from. We're not going to go over that so much here. This is the xmgrace, the Grace website. xmgrace is the graphical version of the Grace software. And for this demo, we're going to be running under OS X, but on a Mac, but it'll run under Windows or Unix, so it pretty much runs the same way. Now, in order to show you some demos, we've created a data file, which is essentially 4 columns of data, TAM delimited data, and that we're going to run that a graph with that. First of all, xmgrace is run from the command line, so we're going to bring up a command line window. And first thing we're going to show you is xmgrace has a large number of command line options. So we're going to type in xmgrace to run the program, and then we're going to use the command line option -help. Whoops. Helps if I type it right. xmgrace help. And it gives you the help, and if you want to see a little bit at a time, you pipe it to more. But anyway, you can see there's a large number of command line options. We're not going to go over that. You can read that documentation. We're just going to show you the basics here. So you type in xmgrace, and it brings up a window. Okay, we'll make it the right size here so you can see the whole thing. Now we're going to now download that data we just created. You go into the data menu, import, ASCII, and then you got to navigate to wherever it's at, and in our case it's in users clean, desktop, example1.dat. Select that, select the file, click OK, and close the window. Okay, there was only what I did there. I made a mistake, which is a good thing. I can show you some other features. It only imported the first graph. Well, I know there's 4 columns in data. What did I do wrong? Well, first I'm going to show you how to get rid of the data that if you put the wrong data in. You can go up to Data, Data Set Operations, select your data set, right-click it, and select Kill. And that will make the data go away. Whoops. Okay, let's do this again. Import ASCII, example date, but what I did wrong was I imported a single set. I wanted to import this as NXY, which is basically the first column's X and then a whole bunch of Y's. And click OK, cancel. Now there's 3 graphs on there. Well, you get all kinds of, we're going to go a few of the features. Let's say, well, this last graph's way near the bottom. So maybe it might be better to do logarithmic scale on the y-axis, let's say. We go to the plot menu, go to axis properties, select the y-axis, and then make it a logarithmic scale. All of a sudden you can see 3 graphs. And you notice you can see that this is a logarithmic scale. Let's say we want to label that axis. We do that in the same menu, axis properties, y-axis. Let's call it y values. Okay. All of a sudden you have y values listed over here. Similarly, we could do the same thing for the x-axis. We could call this x values. Now we have that labeled x values. Now, you could also make the x-axis logarithmic too if you wanted to. And you can see what this data set really is. If this is just, each one of these is a different power of x, the straight lines on a log-log chart. But wait a minute, all my graphs are over here. What if I want to see more detail? Well, you can go back into the axis properties and start the x-axis at, let's say, 1. Come on, there we go. 1. Now you can see more. Okay, what if you want to add a legend to this? Well, this is done by set appearance. Okay, this first data here, or is it this one? Don't know. I can give a legend to it. Let's call this graph. Let's call it graph number 1. Apply. Oh, okay, that's graph number 1. Okay, go over here. Graph number 2. Oh, go back in there. Didn't do the third one. Graph number 3. Okay, now we have a legend, but the problem is our legend is right on top of one of our plots. Well, now we want to go into the graph appearance menu. In the graph appearance menu, you can select legends and legend box, and you can move it around. Let's move this over to the left a little bit, making this like 0.3, let's say. Okay, now the legend's not on any of the graphs. You can move it anywhere in here. And you can also get to it by just double-clicking on the legend if you want. Okay, now the main tab on this graph appearance box, you can give it a title and a subtitle. This is a title. This is a subtitle. Yeah. Okay, that puts a title and a subtitle on the graph. Now you can save this graph. You can go in here and save it, and then you again would navigate and round and find out where you want to save it, but that's not the strength of this software. There's all kinds of things you can do to the graph. You can change the graphs, but its probably greatest strength, in my opinion, is the print setup. All the options, you can print it as PostScript, but you can also EPS, you could write it as a PDF, PNG or a JPEG. So yeah, any one of these options, there are just so many options. You can actually use the command line version of this Grace to generate real-time graphs for websites. These could be used for preparing graphs for publications. Very powerful graphics package. If you want to look at some examples that has some built-in examples, you can go over to the Help menu, go to Examples, which is I guess off the screen for you right now. But there's a whole bunch of example graphs that come with the thing. You can do stacked graphs. You can do one of the examples they show here that's kind of interesting is a map of Australia. Yeah, you can do a lot with this graphics package. So, and why we put it here is because if you're into some sort of field where you have to present data, measurements, it's nice to have a good tool for generating graphs. You can even generate real-time graphs based on measurements on a website. For instance, I've heard of people using this to hooked up to temperature monitors that creates real-time plotting of temperature measurements on a website. Anyway, that's it for this short little demo of this software. Just look in the show notes for where to download the relevant files, and have fun. Okay, now the next thing we wanted to do in this podcast was give you a little short tour of the learningmeasure.tv podcast, or learningmeasure.tv website, and show you some of the things that are on there and how you'd leave feedback. And well, here that is. Here's the learningmeasure.tv website. I wanted to point out this little thing right here that says no comments. Well, on all our episodes and our show notes, which are here, you can leave a comment. You can positive or negative, or you can talk about announcements made in our blog. And how you do that is you click on the episode or podcast thing, and you have to log in. Well, I'll log in, you can actually register down here with the register tab, and it's not that hard, but I've already set up an account. And there you go. Then you can leave a comment. Here is my comment. And then you can submit the comment. Now, it might take a little while, but at this point, it goes into a queue for moderation. We don't want people doing spamming or flame wars, or people saying things like, this is bad, or this is good, or anything like that. Only if you have something to say will we let it get through moderation. Okay, that's pretty much that. Also on the contact page, there's the 3 emails that you can use to suggestions, vendors, and webmaster to communicate back with us. And if you want to learn a little bit more about the site, you can click the About button. And That's pretty much it. Here's all the different podcast directories that the podcast is in, and you can listen from any one of those or iTunes. That's it. Okay, on with our future presentation. And now for our feature. What we're going to do over the next several weeks is go over what I think are an interesting series of topics. Think of this week as laying the foundation for what we're going to be talking about in the next few podcasts. Okay, the first thing we're going to talk about, what is a periodic phenomenon? Periodic phenomenon is something that repeats in time. Well, we're going to talk about the mathematics of periodic phenomena a little bit. Okay, if you have a function f is considered periodic, f of t, let's say, of some time, is considered periodic with period capital T if the condition holds that f of t equals f of t plus capital T for all time. In other words, the function repeats with period t. Now, you might ask yourself, well, if you have a function, if you define such a function, what if you want a function with the same shape, but with a different period, let's say t0. You wanted something with a period t0. Well, a function that has that property would be this. F of t, f of t over t0 t. Because, as you can see, when t equals t0, it equals t. It equals this value here. So from 0 to t0, f of 0 equals f of t, capital T. So this actually is a function that has period t0. Now, one can also talk about periodic phenomena in something called the frequency. Now we're going to use the same symbol here, but you can figure it out from context. 1 over the period is called the frequency. Okay? So 1 over t0, in this case, we'll call f0. So if you, another way to generate a function, one way to generate a function with period t0 was the one we already showed you, f of t over t0 t. But since f0 is 1 over t0, we got a 1 over t0. This is the same as f of t times f0 t. This one's important. We'll see that again. So, of course, another one. Well, okay. So this is a general case for a general function. Now I'm going to change variables now. Do nothing new. Let's say we have another function. This time it's a function of space. We're going to say all the same things over again. Okay, we have a function, g of x. It's periodic in space with wavelength lambda. If this relationship holds for all x, lambda is called the wavelength. There's absolutely no new information here. We just called the variables different things. It's periodic in space instead of periodic in time. We could have used other variables that signified other things and it still would be periodic. Okay, so we can define a spatial frequency as 1 over lambda.
Okay, that's a spatial frequency. It has other names. We're just going to call it that for this purpose. Okay. Now that we have that out of the way, there's a type of function called a sinusoidal function that we're going to talk about. I'll give you 3 examples of sinusoidal functions because there's more than one type, right? Sine x is a sinusoidal function. Cosine x is a sinusoidal function. E to the ix is a sinusoidal function. This is I is the square root of -1. This is a complex number. And you can see that this is equal, by definition, basically, well, not quite, but this is cosine x plus I sine x. Okay. All 3 of these functions and sums of them would all have period 2 pi. So the period for these functions is 2 pi. Okay. Using what we've shown you already, if you wanted to sinusoidal function of frequency or period other than 2 pi, you could do this. Sine or cosine or e to the I 2 pi over the period. Okay, times the time in the case of time. Or you can use sine of 2 pi is the period times the frequency, t. Okay. Both of these represent the same function that's periodic with period t and frequency f. Now, in terms of sinusoid, this combination comes up a lot, and we give it a special name for in time. We say omega is 2 pi f. So we would say this is equal to sine omega t. Okay. If we were going to talk about space for a minute, okay, still sine of 2 pi over lambda x. We're saying the exact same thing as we said here. This gives you something with spatial period or wavelength lambda, which is equal to the sine of 2 pi times the spatial frequency. Now, x. Okay, now this quantity here is given a special name and symbol, k, which is 2 pi over lambda, is called the wave number. So we can say that this is equal to sine kx. Okay, no different content from here. We just change the variable names. So 2 pi over lambda k, 2 pi f for omega. Now, in the cases when you have something that's both functions of time and space, called wave phenomena, which we'll cover next week, there's a relationship between k and omega, and that has something to do with the speed of propagation of the wave. But that's not what we're going to talk about this week. That's what we're going to talk about next week. Okay, we've got these relationships. Now we're going to talk about these various functions here. And I'm going to write some things here. Things to remember. Okay, for sinusoids, we got these terms, omega equals 2 pi f, and k equals 2 pi over lambda. Of course, this is equal to 2 pi over the period, and this is equal to 2 pi times the spatial frequency. Okay, they're exactly the same. They're just given different different symbols and different interpretations. Okay, now we're going to talk about the sign of a function. We'll call this sine of phi of t. Okay. With respect to the sinusoids, sine, cosine, or e to the I, phi of t, this function here is called the phase of the function. Okay, now this function here is periodic only if phi of t is periodic. But even if phi, well, let's look at the case where it is periodic. What we know, or linear, I should say. If this is periodic or linear, this thing will be periodic. Okay. If this is, in the case of just a pure frequency, sine omega t, let's say, the phase is equal to omega t. Well, what is that? Well, if you were to plot phi as a function of t, you can see from this form, say this is t and this is phi, it's a straight line going through the origin with slope omega. See, remember from your algebra, mx plus b, well, b is 0, the slope m is omega. So that means for a change in t, delta t, the slope, right, and you're going to have a delta phi. And the slope, omega, equals delta phi over delta t. Okay. Now if you want to get the frequency out of that, we can solve by using this relationship here, so that f equals 1 over 2 pi. This is the average frequency now over this interval. Delta phi over delta t. Okay, you can also define now the instantaneous frequency by letting delta t go to 0. For those of you who know calculus, then this quantity here is 1 over 2 pi d phi dt, the derivative of phi with respect to time. For those of you who don't know calculus, just think of this as a small change in phi over a small change in t for the moment. This is really the limit of this as delta t goes to 0. Okay, now that's just a linear function in there. Now what do we have for something that's not a linear function? Something that goes like this, let's say. Okay, in this case, the function is not periodic necessarily. It could be, actually. It could be linear or a linear plus periodic or some other such thing. This, you can still define an average omega or an instantaneous omega for the sine function. So you can define the instantaneous frequency for any phi as 1 over 2 pi d phi dt. Now you can never actually measure the instantaneous frequency of anything. But what you can do, well, you can get close to it though. You can measure the average frequency over some interval. So you can, there are devices that used to be in standard labs that were used to compare two accurate time standards, let's say. It's a device called a phase comparator. Here's an example of one. And what it does is it takes two inputs, one from your standard, one from your unknown, and it plots the phase as a function of time, just like on one of these. It's usually done on a strip chart recorder. And then you measure the accumulated phase over some long time interval, long enough so that the uncertainty of the measurement goes below a certain level and in the transfer. And you can still find those in some standard labs. Of course, you can do all kinds of things now. You could, instead of using a chart recorder, you can digitize things. And there are other ways of measuring frequency. going back to the first part of this talk, you could have some periodic phenomenon that, let's say, generated pulses. And you could count the pulses that generated by one compared to the pulses generated by the other for some set of pulses from the first standard. And you look at the difference and you can come up with a frequency difference. Now the phase comparator way of measuring frequency, let's say a little bit more about that. Again, you're going to measure frequency, which is equal to delta phi over delta t times 1 over 2 pi. Well, there's going to be some uncertainty with each phase measurement, right? So it's standard uncertainty analysis techniques, delta f equals, well, delta f over f, the fractional frequency error or whatever difference is going to be the uncertainty in the phase over that 1 over 2 pi delta t. Plus 1 over 2 pi delta t over delta t. Okay. Actually, no, the 1 over 2 pi's cancel. Forgot about to do that, right? Okay. So this function, if this phi gets big enough, this term goes down. So in other words, you have to wait a long time. Again, if delta t is long enough, this time this gets real small. So to get this as small, you can make this arbitrarily small by just waiting a long time. Of course, in the real frequency measurement, there's another term that you got to take into account, and that's the uncertainty of your standard. The limiting factor is the uncertainty in your standard. There's another problem. That is somewhat true that although your accuracy gets better for the average frequency, both standards could be drifting. So you could have an issue where this gets extremely accurate, but it's no longer representative of the frequency that your standard's putting out. That'll be a topic of another discussion on another podcast. Like I said, what we're doing here is the mathematical foundations for the next several podcasts. Hope you enjoyed this one. And again, if you have any suggestions on what topics, or even some questions that you'd like answered on some measurement topic, we'll find somebody to answer it if we can't find, if we don't know the answer now. Send your questions and your suggestions to suggestions@learningmeasure.tv. Again, if you're somebody, a vendor, or somebody with a service you want to market, give us an email at vendors@learningmeasure.tv and let us know what you have in mind. Again, if you want to get on our podcast as a consultant, join our consultant network, and you'll be entitled to an interview on the podcast. All right, until next time, have a good week.